So at the top of page 8, we're going to practice evaluating limits. And so in our notes, we already have the benefit of knowing that these functions are continuous at this particular value, but we won't always know that. So anytime we evaluate a limit, the first thing we're going to do is we're going to plug in the value. So if I want to evaluate the limit of x squared plus 1 over x minus 3 as x approaches 2, we're going to start by just plugging in a 2 for x and seeing what happens. So I get 2 squared plus 1 over 2 minus 3. So that is, let's see, 4 plus 1, so 5 over negative 1, and we get the number negative 5. So when we plug 2 into our function, and we get the output, negative 5, when we're evaluating the limit, that's how we know that our function is continuous. So negative 5 is the evaluation of the limit as x approaches 2. All right, try the next one, pause the video, and then resume after you've tried it. When we plug in 3 pi over 4 for that second example, we end up getting a complex fraction, root 2 over 2 in the numerator, because that's the sign of 3 pi over 4, over the denominator, 3 pi over 4. So a quick and easy way to get rid of this complex fraction, there's a few things we could do, but we could just multiply the top and the bottom by 4. And the reason that'll help us is it will clear both the denominator in the bottom and the denominator of the fraction in the numerator. So we could also multiply by the reciprocal of the denominator. I kind of like doing it this way. So root 2 over 2 times 4 is 2 root 2, and 3 pi over 4 times 4 is just 3 pi. So that is a faster way, in my opinion, to arrive at what we might consider a more simplified answer. Okay, so in our next set, we're going to work with some functions that may have a jump. So remember, a jump can only occur at the boundary of a piecewise function. So when we're not working with piecewise functions, we don't really have to worry about jumps. So again, when I say the boundary, and there could be multiple boundaries, this function, the boundary is at, the function changes where x equals 4. So x equals 4 is considered the boundary of this piecewise function. So we're still gonna evaluate g, the limit of g as x approaches 4. But since we already know that that's the boundary of a piecewise, we have to break it into two one-sided limits. So let's start with the left. So if you get confused about like left and right of 4, just think of a number line. What types of numbers are to the left of 4? Well, how about like the number 3? So all of those values to the left of 4 are values where x is less than 4. And then on the right-hand side of the 4, like say 5 or any other number, would be values where x is greater than 4. So I know that on the left side of the 4, I would be using the top part of my piecewise function because that is the function I use when values of x are less than 4. So the limit of g as x approaches 4 from the left. So not negative 4, but we put the negative symbol after the 4 to indicate from the left. And again, I'm going to just start by plugging 4 in to this expression 8 minus x squared. So this becomes 8 minus 4 squared, which is, of course, 8 minus 16, which is negative 8. Now we also need to consider the limit from the right. So the limit of g as x approaches 4 on the right-hand side. Well, now we're going to use the bottom piece of this function, x squared over x minus 6, because if we're coming towards 4 from the right, we're approaching 4 with values of x that are greater than 4. So that's why we have to use this bottom piece. All right, so same thing. I'm going to use x squared over x minus 6, but I'm going to substitute 4 for x. So 4 squared over 4 minus 6, which is 16 over negative 2, which is also negative 8. So remember, the definition of a limit exists if the limit from the left and the right agree. And so in this case, they do. We get the value negative 8. Therefore, we could conclude, oh no, what's happening? Therefore, we could conclude, oh no, exit drawing. Sorry, I'm not so good with the screencast. That the limit of g as x approaches 4 is negative 8. Now, we're also asked to evaluate the limit of g as x approaches 3. Now, 3 is not the boundary of the piecewise function, so we don't need to consider the limits from the left and right. Since 3 is less than 4, we'll use the top piece of the function. So I'm going to evaluate the limit of g as x approaches 3. So I'm only substituting that into 8 minus x squared. So that becomes 8 minus 3 squared. So 8 minus 9, and we get negative 1 for that. Now, it's also possible to have a hole in our piecewise function, and in this next example, we might find that. We might not, though, so let's see. So if we evaluate the limit of f as x approaches e, let's see what we get. So again, we want to evaluate the limit as x is approaching e, not necessarily where x equals e. If I asked you to just evaluate the function, if I said what is f of e, well, we know when x is equal to e, f of e yields 4. But if I want to evaluate the limit as x is approaching e, if we think about where e is on our number line, if I'm approaching e, I'm coming at it from values that are less than e or values of x that are greater than e. So I don't want the value at e, I want to know what's happening to the graph of the function as we're getting closer to e on either side. Therefore, we want to use the top part of our limit for all these values of x that are not equal to e. Sorry, the top part of our function, not the top part of our limit. All right, so the limit of f as x approaches e, we're going to use 3 times the natural log of x, but in this case, the natural log of e minus 1. So remember that the natural log of e, and I could think of that as e to the first power, is 1. Similarly, the natural log of e, let's say cubed, for example, is 3. So because natural log and an exponential base e are inverses, what we get is we get just that number 3. We could be more general and say the natural log of e to any power n yields n. All right, so that was just a little algebra review. So 3 times the natural log of e is really just 3 times 1, and then we still have to subtract 1. So we end up getting 2. So even though the function evaluated at e is 4, the limit does exist. So the limit of f as x approaches e is just the value 2. So what do these things mean? I know this isn't the question we're asked explicitly in our notes, but we could conclude that our function f is not continuous at e. Instead, though, the limit does exist. The limit is 2. The function is equal to 4. If you're wondering what the graph of this function f would look like, it's really hard to see in Desmos. So this red curve, this represents 3 times the natural log of x minus 1, but really on a graph, When we get to this value where x equals e, and remember e is about 2.718, etc., and some change, we would actually have a hole in our graph. So right around where my cursor is, there would be a hole. And up here where we see this dot filled in, that's the value e comma negative or comma 4. So really, this function behaves like this logarithmic function, except where x equals e. And instead, this function exists up here. So that's what it would look like for this graph to not be continuous at e, but to have the limit exist. Unfortunately, Desmos isn't great at showing us holes in the graph, and really neither is the TI calculator. We just have to know and understand what's happening there. All right, we're going to skip this absolute value example. We could break that out into a piecewise function, but for time, I'm going to skip that one in this video.